Welcome back to this NPTEL online certification course in molecular rearrangement and in reactive intermediates. In the last class, we have learned about the single electron reduction using this sodium, lithium. We have learned about the Birch reduction, and in the today's class, we are going to learn about another important concept in the radical chemistry, which is called hydrogen atom transfer. I have used this terminology several times before. I have when I was teaching you the Barton decarboxylation, I also talk about hydrogen atom transfer. I was trying to talk about the tributyltin hydride, there also I talk about the hydrogen atom transfer. But now I am going to briefly talk about what is the definition of hydrogen atom transfer and how that reaction is useful in the radical chemistry. So, let us start with the content for today's topic. So, in the today's topic we are going to talk about the definition and some of the details and some of the basis about the hydrogen atom transfer, and then I am going to talk about two important name reaction. One is the Barton nitrile ester reaction and the other one is the Hofmann-Loeffler-Fertig reaction. And then I am going to talk about some of the modification and some more examples. So, first thing is let us talk about what is the definition of hydrogen atom transfer. So, the most important thing is in this reaction you will find there will be hydrogen atom donor or hydrogen donor, there will be hydrogen abstractor, and then at the end again what is going to happen, you can see this will lose the hydrogen, it will form this radical and it will take the hydrogen from the BH. Okay. So, it is where a neutral hydrogen atom is removed from a substrate to another molecule. Okay. That is the important thing here. Now, if you look into this reaction about the thermodynamics, then one of the important thing is to get this reaction towards the product, you have to understand that we already learned that in the radical reaction. If you remember when I was talking about this some sp3ch bromination using the chlorine radical or the bromine radical during the bromination or chlorination, then you have we always talk about that when the bond is forming, which bond is breaking and which bond is forming, what is their bond dissociation energy. That means the thermodynamics always the newly formed BH bond has to be strong than the CH bond to cleave or to provide the driving force, as you know from the thermodynamics, that if this bond is the stronger bond compared to the starting one, that will give you the driving force for the formation of the hydrogen atom transfer. But again that is not the only factor, that is the bond dissociation energy. There are several different factors which I am going to explain. But before I go to them, I just want to give you a summary of what are the different hydrogen atom abstractor used for the hydrogen atom abstraction. You have seen that the alkoxy radical which can be formed from the corresponding from the pyrolysis, and then you have seen about the halogen atom, the halogen radicals, when you talk about the corresponding the bromination chlorination reaction. Then there is another important is the thiol radical. I am going to talk about thiol radical, and then there will be aminoxyl radical and then the carbon center radical. So there are more, I am just trying to give you some of the common one. Then there are some hydrogen atom donor. I am sure you guys have seen about the tributyltin hydride before, when I was going to talk about, when I already talked about the Barton decarboxylation reaction. Then triethyl silicol hydride. Okay, so these silanes are very useful. I think I am going to explain them again when I am going to talk about the silicon chemistry, that why that this type of compound is a very useful compound for and used as a hydrogen atom donors. Then there are some variation here. This is the TMS3 SiH. You can draw like that. There are so 3 silicon group with the 3 methyl. So that means with a hydrogen here. Okay. And then we are going to talk about the RSH, again thiols. I am going to talk about that they are also very good hydrogen donor. Then there will be some example with alkane and alcohol. Okay. So the important thing is when I talk about the hydrogen atom abstractor and hydrogen atom donor, there is one of the things I have already mentioned in the previous classes, that the radicals can be classified as a electrophilic radical or nucleophilic radical, if you remember. And then the question comes that if there is a electrophilic radical, then it will prefer to abstract hydrogen from a nucleophilic hydrogen atom donor. And if you have an electrophilic radical, then it will prefer to abstract hydrogen from a nucleophilic hydrogen donor. So let us try to understand what I was trying to talk about. But in this part also what I am going to cover that this type of hydrogen atom transfer between this donor and acceptor, as I was telling you, can be. So there are several different effects, which is the most important factor why this hydrogen transfer is happening. So, there are structural effects, there are solvent effects, stereoelectronic effects, polar effects and strain related effects. So, I try to give you some example to understand how these effects are useful in the hydrogen atom transfer reaction. So, first thing is, as I was telling you, that there is a electrophilic hydrogen donor source and there is a radical which is nucleophilic, or if you have a electrophilic radical, then it will prefer a nucleophilic hydrogen source. But the problem is, if there is a scenario here, there is a nucleophilic radical here, as I was telling you, you guys remember that if you have alkyl radical with 3-methyl or 2-methyl or primary, or so this primary, secondary, tertiary, these two radicals are nucleophilic radicals. I have already explained them. So, now if you want to abstract a hydrogen from a nucleophilic hydrogen source like triethylsilyl hydride, or you can see from tributyl hydride also, then what is going to happen? There is a polarity mismatch. As I was telling you that it will be preferable, it will go from the nucleophilic can abstract from a electrophilic hydrogen source. So, how to solve this problem? How to get this reaction going? The only way to get this going, if you can put some of the thiol here. So, what is the role of thiol? Now, thiol can able to go for the reversal of polarity, that is the important thing. Okay. So, adding thiol can improve the yield of this reaction. So, now we try to understand what is happening by this polarity reversal catalysis. Okay. That is a very important terminology in the hydrogen atom transfer chemistry. So, what is happening here? I am showing you there is a nucleophilic radical and a electrophilic hydrogen. Now, once you use a thiol, these are electrophilic hydrogen donor source. So, what is going to happen? This reaction will be favorable because you are forming a more stronger bond here. You are forming a RH bond which is a stronger bond, and you are generating an electrophilic radical here. Okay. So, now what is happened? This reaction become favorable. So, there is a polarity match here in this one. Now, what is going to happen? As you are generating a electrophilic radical, that can able to comfortably take the hydrogen from this nucleophilic hydrogen donor. Okay. And then going to generate this corresponding SH and this triethyl silicon. Again you can see there is a bond energy difference here. The sulfur hydrogen bond will be more stronger than the silicon hydrogen bond. So, that is another driving force here. Okay. So, the polarity match is important. If there is a not polarity match, then this polarity reversal catalysis can be useful. So, here I think I am going to give you the example again for another reaction here. So, what is happening here? It is a this carbon bromine bond is getting cleaved to replace with a carbon hydrogen bond. Okay. So, what is happening? Triethyl silicon hydride is the hydrogen donor, and DLP is the corresponding peroxide which is a initiator, which is actually cleaving this carbon bromine bond. So, this peroxide oxo radical going to cleave this to generate a radical here. Now, this radical species going to get a hydrogen source, okay, not from directly from the silicon hydride, because you are using the thiol in 1 mole percent as a polarity reversal catalysis. So, previously if you do not use thiol, means without, I can say without RSH your yield is 10%, and once you add this 1 mole percent of corresponding thiol, your yield is 99%. So, you can see the what is the difference. Okay. Again I think there are some report also that people have replaced this corresponding tin hydride, as I was mentioning that tin hydrides are toxic. So, that can be replaced by corresponding silicon hydride as well. This type of silicon hydride species called silane. So, they are very good hydrogen donor source. So, now I am going to talk about some of the effect. I mentioned there are some polar effect under the structural effect. You have seen there are some polar effect, stereoelectronic effect. So, first thing is this type of radical which is called you can see here under H nu this oxygen bond is the weaker one getting cleaved. So, under the laser photolysis it is generating this corresponding radical here, and as you know this type of oxo radicals can be, if you change this R by methyl, then it will be this terbutyl oxo radical here, terbutoxide radical, or if you have a phenyl here, this is called the cumyloxyl radical. Now, the important thing about this cumyloxyl radical here, this radical is characteristic by an absorption band in the visible region of the spectrum. That makes it perfectly convenient to study some kinetics. So, that is why this radical I am going to show you in the couple of slides, where this cumyloxyl radical was used for the measurement of the reaction rate for different type of hydrogen atom transfer reaction. Okay. So now you can see that I am going to show you some example here. You can see we have a cyclohexane here, we have a CH3CN and then CH3COCH3 acetone. So acetonitrile, then acetone, and then you have a cyclohexane. So now once you are trying to understand their bond dissociation energy, this bond is stronger. So this will be stronger than this one, and this will be stronger than this one. But what is happening in the hydrogen transfer rate? You can see the hydrogen transfer rate is higher here compared to this one and compared to this one. So these two looks very similar, but this one is higher than this. So what is happening here? You see we are cleaving a stronger bonds compared to a weaker bonds. Okay. So although it's looks like that, but now if you try to think about that your radical, what is your radical here? So as I mentioned that this is a radical which is a electrophilic radical. Okay. So if you have a electrophilic radical, then it will prefer for hydrogen abstraction from a nucleophilic hydrogen source. Now if you compare between this cyclohexane to this CH3CN and acetone, as you are having electron withdrawing group attached with this CH3, because this abstraction going to happen from this CH3 only, you have a CH3 with a electron withdrawing group. Now this hydrogen atom abstraction going to happen from the CH3, as you have electron withdrawing group, now this hydrogen will be not that nucleophilic hydrogen donor compared to the CH bond in this cyclohexane. Okay. So that is why this is going to get cleaved first compared to the CH3CN versus the acetone. Again there is this the same example here. If you use this tarbutaxide radical, and if you have a primary versus secondary and tertiary alkane, what is happening? You can see the alkane, the rate is so if you have a primary, then secondary, then tertiary, and you are abstracting this CH, then the rate is 1 is to 12, around 12, and then around 44. So what is happening here? Again you can see from primary to secondary to tertiary, what is happening here? Again you can clearly see that the CH will be more hydrogen. So that will be kind of, you have a more electron rich, that means that will be a better nucleophilic hydrogen donor. So that is why this the tertiary will be, tertiary CH is going to be going to get cleaved or going to get participated in the hydrogen atom transfer faster, because that the tarbutaxide is already a electrophilic radical. And again very similar type of example here. What is happening? You can see here again you have this cyclohexyl here, then you have a benzylic and you have a toluene CH. Again you can see the rate is higher here compared to these two. Again if you have a more stabilized radical, so you have to also understand the bond dissociation energy, and at the same time that what type of radical is forming at the end. Okay. So here again what is going to happen, this as I mentioned, the KH with increasing the bond strength was observed for substrate with CH bond dissociation energies greater than 92. That means once you see here again the factor which I mentioned, that the hydrogen which is going to get cleaved, if that is a more nucleophilic, then that will be cleaved faster. Then there is another effect, polar effect controlling hydrogen atom transfer. So here you can see what we are talking about, abstracting of this. So abstracting of this hydrogen here. So in these three cases, if you see this in these three amino acid, going from glycine to valine, what is happening? This hydrogen atom transfer rate is looking almost similar. But once you come to proline, you see the rate is higher. You can see almost like so if you compare them, then this rate is much higher compared to this one or compared to others. So what is happening in case of proline? So the thing is, you might be looking into this. If you try to think about that, in case of proline, you have to understand that there are some other hydrogen atom here which can be also take part. That means they are saying that these hydrogen here are actually getting abstracted compared to this hydrogen here, okay, which is actually deactivated due to the presence of carbonyl group. Now what is going to happen, because these hydrogens you are attached with the nitrogen, and here what is going to happen? So these these are the CH bond which is actually next to a heteroatom. So that means if you have a scenario here that you have a X and you have this hydrogen, if this hydrogen getting abstracted, then you have to understand there is a this the lone pair of this X can give electron to the corresponding sigma star of this CH, okay. So make it more activated for the hydrogen atom transfer. another example of tributyl hydride. So we have learned about tributyl hydride is also used, very much used for the hydrogen atom donors. Now you can see the difference for the reaction where you are actually converting from this corresponding R dot plus Bu3 SNH. So this is the reaction we are talking about, and you are forming this RH and Bu3 SN dot. Okay. So in this reaction we are trying to compare the rate here. Now you can see here, if you have a phenyl or if you have vinyl radical, then the rate is 5.9 into 10 to the power 8. But once you come to some sort of a alkyl radical here, it is much lower. So what is happening here, that once you have a aryl or vinyl radical, they are very reactive. Okay. So once you are generating a highly reactive radicals, then these radicals can react much faster because they are reactive radical. If you talk about tributyl hydride, this is a nucleophilic hydrogen donor source. So now these radicals are very reactive. This is going to abstract hydrogen from the tributyl hydride. That's why this rate is much higher compared to this. Okay. There is a important stereo electronic effect, as I was mentioning, that in this particular scenario you can see here what is happening. Here you have this amide, in this amide nitrogen you have this ethyl group here, here you have a isobutyl group here, and here you have a pyrrolidine. So what is happening here, once you are talking about the hydrogen abstraction rate using this radical, this oxo radical, then here the rate is much faster. So this was hydrogen abstraction is much faster compared to others. So what actually they are trying to explain this result, they are saying that for the hydrogen atom abstraction, once you talk about the this compound and once you try to draw the conformation here, we are talking about abstraction of this corresponding hydrogen here, and is saying that in this alpha CH bond are held in a conformation where they are optimally aligned to the pi system. So they are saying this bond is optimally aligned to this pi system here. Okay. So that means there is a some sort of a secondary interaction, that there is a this pi electron is going transfer into the there is this sigma electron getting transferred to the some sort of a pi star electron. So this CH is getting weaker, that is why this hydrogen abstraction is faster. Again there are solvent effect. So the idea is, if you are using a polar solvent versus a polar protic solvent versus polar aprotic solvent, what is happening here? Because once you know that if I am going to compare that THF versus this one, let us try to compare them. So if I try to draw a tetrahydrofuran here, so now we are talking about the hydrogen atom abstraction of this same thing here, this hydrogen we are trying to abstract. Now if you have a scenario where you you do not have a hydrogen bonding and here you have a hydrogen bonding, what difference is going to make? Because once you have a hydrogen bonding here, this is going to form hydrogen bonding is this hydrogen atom acceptor oxygen. So once you form this hydrogen bonding here, in this case, or if you have a triethylamine, very similar situation. Once you have a hydrogen bonding, then there is a generation of some sort of a delta plus charge. Now this thing what I have mentioned here, that there is a electron donation from this N2 corresponding sigma star, correct, this non bonding to the sigma star. So that will be hampered here once you have a corresponding hydrogen bonding. That means once you have a hydrogen bonding going to be hampered. So here, because of this N2 sigma star electron donation, this bond will be somewhat activated for your hydrogen atom transfer, but here it's that possibility will be decreased, that is why it will be less activated compared to this. So the hydrogen atom transfer the rate will be faster in THF compared to THF with a polar protic solvent, or with the same thing for the triethylamine. So I talk about some of the important the fundamental about the hydrogen atom transfer. The one of the important fact is there will be a lot of time I am going to talk about some intramolecular hydrogen atom transfer, and this is mostly controlled by 1,5 hydrogen atom transfer. You will see that this 1,5 hydrogen atom transfer going to control the major intramolecular hydrogen atom transfer, and you will see only few cases there is a 1,6 where they use this silicon, or there will be this 1,7 where they use this aryl sulfonyl tether. The question comes that once you have this 1,5 hydrogen atom transfer, the question always arises that why not 1,4, why not 1,6. Of course, this answer of this question was given mostly by the theoretical calculation, where they found out this 1,5 hydrogen transfer is favored because of formation of this 6-member chair like transition state. But once you come to this 1 per hydrogen transfer, there is a major thing, the enthalpic barrier. Okay. So, the enthalpic barrier is 6.6 kilocalorie, which actually preventing this 1 per hydrogen transfer. And once you come to 1,6 hydrogen transfer, you can see now in case of 1,6 the entropy playing a role. Again, the entropy of the reaction can be depend on a lot of other factors. So, this entropic factor is actually stopping this 1,6 hydrogen transfer to happen. Okay. So, now I am going to talk about the important reaction called the Barton nitride ester reaction. Okay. So, what is happening here? In this reaction, if you see starting from this corresponding alcohol, in presence of the NOCl and pyridine, it is forming this nitride ester, and then it is forming the corresponding hydroxyoxime here in this particular position. So, what is happening? There is in this reaction there is a hydrogen abstraction happening from this particular position. So, you can see here this is alpha, beta, gamma and delta. So, this hydrogen is getting abstracted to form this corresponding hydroxyl oxime. Okay. And again I think Barton have received Nobel Prize in 1969. He has done several contributions in the radical chemistry. So, let us try to understand what is happening here. Once you forming this compound here, this nitrite, what is happening here under the H nu means once you put the UV light here, that is going to cleave this nitrogen oxygen bond here to generate this oxygen radical here, which is going for this 1,5 hydrogen abstraction. As I mentioned in the previous slide that there is a 1,5 hydrogen abstraction is the important factor for the intramolecular reaction. So, that is going to generate this radical species here, which can go for a radical recombination. Okay. Then after the tautomerization, it can form this corresponding oxime. Okay. So, it is a first is the photochemically induced cleavage of the nitride O bond, typically using a high pressure mercury lamp, then formation of the alkoxy radical as I mentioned here in this step, and then the recombination of this nitrosyl radical. So, that is very important, that which is getting broken here getting again recombined, and then finally the radical recombination and then the tautomerization giving to the product. You can show here starting from this in this condition first generating the radical 1,5 hydrogen extraction, and then now if you use a I2 as a competing radical source, then this in this step what is going to happen, it can form this corresponding iodo compound here which can participate in the SN2 reaction. So, this oxygen now can attack here SN2 reaction, get rid of iodine to get to this corresponding byproduct. Okay. If you want that, you can use the iodine to get to that compound. So, now we try to understand here, you have a OH group here. So, first thing is NOCl pyridine formation of this compound. Now, you can see, so this is going to abstract this. So, you can see this OH going to abstract from the corresponding methyl which will be on the same side. If you try to draw the particular conformation of this compound, you will see that this is the OH and the methyl will be the same side. So, this can abstract the this hydrogen from this type of cis-OH conformation, and then it can get to the corresponding product here. Here again you can see here in this example also we are seeing the very similar things here. First formation of this nitroso which can able to take the proton from this particular position. So, sorry, no, not a proton, there is a hydrogen abstraction happening from this position. So, this is a again this is a 1,5 position here 1 2 3 4 5. Sorry, 1 2 3 4 5, okay, to formation of this product here. There is another example, very similar example in the previous slide we have seen. First there is a cleavage formation of this oxo radical which is in the same side of this CH3 going for a hydrogen atom abstraction, going to make this CH2 dot, it is going for another sequential hydrogen atom abstraction, okay, to form this product, or it can go for this first hydrogen atom abstraction and go to this product. Then I am going to talk about the another important reaction which is the the Hofmann-Loeffler fatigue reaction. Here what is happening, this is another important reaction. You start from this N halogenated amines and you are going to convert to the cyclic amine here. Okay. So, in this reaction what you need, in this reaction need a halogenated amine in a strong acid, okay, that is the, and then you need to irradiate using ultraviolet light. Okay. So, what is happening in this reaction? First thing is the protonation. As you have a strong acid, it is going to protonate this corresponding N halogenated compound. Then under this UV light, this the nitrogen and the halogen bond going to get clipped to generate the X dot, okay, and then generate this corresponding N dot. So, it is a, as I said, this is a a charged species as well as a radical species on the nitrogen, which you can see in the next slide. From there it is going to go for a 1,5 hydrogen abstraction, okay, and then it is going to form this alkyl radical, and then this alkyl radical can take this X from here to form this species, and which can finally going to, there will be proton abstraction from this nitrogen using a base to generate this nitrogen, which has a lone pair which can attack here from SN2. So, now what is going to happen? You can end up forming a pyrrolidine. So, starting from a linear compound, you end up making a cyclic product. Again there is a the radical attack exhibits strong preference for the secondary over the primary. That means, what is happening, if there are two different positions where the radical can be formed, then it will prefer going for the secondary over the primary. As you know, the stability of the radical is the important factor. Okay. So, here this result suggests the high selectivity for the third degree hydrogen over the others. Here what is happening, the preferential abstraction gamma hydrogen atom correspond to a 6-member tangent state. So, that is also very important factor here. It is going for the hydrogen atom abstraction, it is going for forming of this 6-member tangent state, and that is how this product is becoming the major product compared to this one. So, we are talking about that why not in the next one, why not it is forming going for abstraction from this one, okay, because here the 6-member tangent state is the favor one. There is an example here, again it is a modification using PIDA and iodine. Here first thing is the formation of this Ni, which is going to get oxidized to form this N dot. From there it can go for this 1,5 hydrogen atom abstraction. So, 1,5 hydrogen abstraction to make this dot, which can combine with the I dot to make iodine, then internal attack for to get rid of the iodine and get to this product. Another example here with the PIDA and iodine, here you can see in this molecule you have this compound here, which can be, you have amine there. So, PIDA and iodine, it will form this Ni, then going for making the dot, and then it is going for the hydrogen abstraction, and finally I dot, and then cyclization, which can go to this this product. Okay. So, this came in the exam. So, as I mentioned, I have also tried to give you some example from the exam. Another example here, we can see here from this compound, if you use tibutyltinated and AIBN, if you remember, AIBN going to make this radical going for hydrogen atom abstraction, making the corresponding tin radical, which is going to clip this carbon bromine bond. So, there will be debromination to generate this radical 1,5 hydrogen abstraction, generate this radical. Then there is a exoteric cyclization, which I am going to explain in the next class about the intramolecular radical cyclization to form this product after the hydrogen abstraction. Here another example, you are forming a vinyl radical under the radical initiator source. Then what is happening there is, so if your Y is oxygen, then there is no way there is a 1,5 hydrogen. So, that is why it will going to go for a 1,6 hydrogen shift, and then there will be intramolecular radical cyclization, which I am going to explain, going to form this compound. Again there is another example here, you have a NR which can generate a radical, then it will be, so there will be 1,6 hydrogen atom abstraction, as there is the 1,6 is more favorable here to form this corresponding product. Okay. So, again this came in the exam that if you start with this compound, what will be your product. Again if you try to draw this one, that is there is a 6 member here and a 5 member. Now, you can clearly see that this will be the position where the hydrogen atom abstraction going to happen to form this compound, which are in the H3O plus going to form the corresponding ketone. Another example here also you can see that if you try to draw them in this particular conformation, you can clearly see that this is going to abstract from this methyl hydrogen, going to be hydrogen abstraction going to happen to get to this product. Under if you put H3O plus, it will go into the corresponding aldehyde. Another example came in the gate here. What are you going to see here? You have this OH group, and then you have this methyl. So, OH is going to form the corresponding NO, going to go for hydrogen atom abstraction from the methyl, 1,5 hydrogen atom abstraction, and then if you put the the hydrolysis condition, then it will go to corresponding aldehyde. Another example here in this compound, again you have this N bromo, which is going to go for hydrogen atom abstraction. So, there will be again 1, 2, 3, 4, 5, 1 5 hydrogen ester get this corresponding bromide, and then what is going to happen? It can go for intramolecular cyclization to form this product. So, I hope in this class I talk about the some of the basics of the hydrogen atom transfer. I talk about 1,5 hydrogen transfer, and under that category I talk about the Barton nitride ester in reaction and the Hofmann-Loeffler-Fertig reaction, and some of the modification. Here are some that textbooks you can follow, and then thank you for coming to the class, and I am going to see you guys in the next class.